CO2 corrosion or sweet corrosion. CO2 corrosion, commonly known as sweet corrosion, is a critical issue in oil and gas operations, particularly affecting carbon steel and low-chromium steel components. This type of corrosion occurs internally within piping and equipment when free water containing dissolved CO2 is present. The process begins when CO2 gas dissolves in water, forming carbonic acid, which lowers the pH and aggressively attacks steel surfaces. Unlike dry CO2 gas, which is non-corrosive, the presence of water is essential for corrosion to occur. This phenomenon is prevalent in systems where condensation forms due to temperature drops below the dew point, creating localized areas of free water. The resulting corrosion can lead to thinning of metal walls, leaks, and catastrophic failures if not properly managed. Understanding CO2 corrosion is vital for maintaining system integrity, reducing downtime, and ensuring operational safety. It is a complex electrochemical process influenced by environmental and operational factors, making proactive monitoring and mitigation strategies indispensable in industries such as oil and gas, petrochemicals, and power generation. Prerequisites for corrosion occurrence. Two primary conditions must be met for CO2 corrosion to occur: the presence of free water and the use of susceptible materials. Free water acts as the medium for CO2 dissolution, forming carbonic acid that initiates corrosion. This water may enter the system as liquid or form as condensate when operating temperatures fall below the dew point of the fluid mixture. The location and amount of free water significantly influence where corrosion develops. The second condition involves material selection. Carbon steel and low-alloy steels with less than 13% chromium are highly vulnerable to CO2 corrosion. These materials lack sufficient resistance to acidic environments created by carbonic acid. In contrast, stainless steels with higher chromium content or exotic alloys offer better resistance and are often employed in systems where CO2 corrosion cannot be mitigated through operational controls. Recognizing these prerequisites is essential for designing effective prevention strategies and selecting appropriate materials for long-term reliability. Environmental and operational factors. The severity of CO2 corrosion is governed by multiple interrelated factors. Temperature plays a significant role, with corrosion rates increasing as temperature rises up to approximately 150 to 175 degrees Celsius or 300 to 350 degrees Fahrenheit, beyond which CO2 solubility decreases, reducing corrosivity. Pressure, specifically CO2 partial pressure, is another critical factor. Higher partial pressures result in more dissolved CO2, lowering pH and accelerating corrosion. Fluid flow rate also impacts corrosion by stripping away protective layers such as iron carbonate scales and enhancing mass transfer of CO2 to the metal surface. pH levels directly influence the aggressiveness of the environment, with lower pH correlating to higher corrosion rates. Under certain conditions, protective phase CO3 scales can form, significantly reducing corrosion if they remain stable. Additionally, chemical inhibitors are commonly used to create protective films on metal surfaces, mitigating corrosion. Understanding these factors allows engineers to predict corrosion behavior and implement targeted control measures to maintain system integrity. Mitigation strategies, approaches to control CO2 corrosion. Mitigating CO2 corrosion requires a combination of material selection, operational adjustments, and chemical treatments. One of the most effective strategies is the use of corrosion inhibitors, which are injected into the system to form a protective film on steel surfaces, reducing direct contact with corrosive fluids. Material upgrades, such as employing stainless steels with chromium content greater than 13% or using specialized alloys, provide inherent resistance to carbonic acid environments. Operational controls, including managing temperature and pressure to minimize condensation and CO2 solubility, can also reduce corrosion risk. Additionally, maintaining optimal pH levels through chemical buffering helps limit acidity. In systems where protective phase CO3 scales can form, conditions should be optimized to encourage their stability. Regular monitoring using techniques like corrosion probes and inline sensors ensures early detection and intervention. Implementing these strategies collectively enhances equipment longevity, minimizes maintenance costs, and ensures safe and efficient operations in CO2-rich environments.